A plant that costs barely $5 from the garden section can slash wall temperatures by as much as 28 degrees Fahrenheit. On a west-facing exterior wall, it can reduce the cooling burden by almost 1/3. No electrical wiring, no compressor humming through the night, no energy bill attached to it at all. Just roots anchored in soil and layers of leaves climbing across brick and siding. That plant is common ivy. You've seen it before. Draped over old cathedrals, wrapping around university buildings, hanging across storefronts in Europe. Yet almost nobody looks at it and thinks of climate control. And the reason has almost nothing to do with whether the system actually works. When people talk about heat entering a house, the conversation usually revolves around roofs and windows. But the biggest surfaces exposed to direct sunlight are often the walls themselves, especially those facing south and west. By the middle of a July afternoon, exterior siding can hit 150 degrees Fahrenheit. That heat slowly pushes inward, crossing sheathing layers, insulation, and interior surfaces, until every room behind the wall begins to warm. Your air conditioner spends the entire day battling that transfer. Across the average household, heating and cooling together now consume more than $1,000 every year. Yet almost nobody inside the building industry wants to acknowledge that part of the answer may already be growing outside. And the evidence is not theoretical. The Royal Horticultural Society partnered with the University of Reading in a controlled experiment published in the journal Building and Environment. Researchers tested 3 separate climbing plants on model building structures specifically designed to isolate thermal performance. Ivy delivered the strongest results of all 3 species. Internal wall temperatures dropped by 7.2 degrees Celsius. That translates to roughly 13 degrees Fahrenheit inside the structure itself. On the exterior surface, temperatures fell another 5.7 degrees. But the detail that should have completely changed public perception came from another measurement entirely. Humidity inside the building did not rise, it fell. That matters because the most common fear surrounding ivy has always been moisture damage and damp walls. Yet the study recorded the exact opposite outcome. Another experiment published through heat transfer research on a real 2-story structure covered with dense ivy growth, focused specifically on energy flow. The wall faced west under clear summer conditions. Results showed the vegetation cut the peak cooling load through that wall by 28%. Not just lower surface temperature, lower energy demand itself. Nearly 1/3 of the workload normally pushed onto the air conditioning system was absorbed naturally by a layer of leaves. Then came the research that changed the discussion entirely. Professor Heather Viles at University of Oxford led a 7-year investigation funded through Historic England, previously known as English Heritage. The project monitored ivy growth on walls throughout the country. Research sites stretched across Oxford, Dover, Bristol, Yorkshire, and Leicester. The findings were difficult to ignore. During hot weather, walls covered in ivy remained 36% cooler compared to exposed masonry. But winter produced an equally important discovery. Those same walls stayed 15% warmer during cold conditions. The plant was not simply cooling buildings during summer, it was also adding insulation through winter. One living layer performing 2 entirely different seasonal functions. The Oxford team later published freeze-thaw data in scientific reports, part of Nature's journal network. Sensors revealed that ivy reduced the frequency of freezing events by 26%. The total duration of those freeze cycles dropped another 34%. Their intensity declined by 32% as well. In practical terms, the plant was helping prevent long-term structural cracking caused by repeated freezing and expansion inside masonry. While instruments remained attached to the walls, researchers identified another effect almost nobody discusses. Ivy behaved like a particle trap. Fine and ultra-fine pollution particles, including contaminants smaller than 2.5 microns, accumulated at densities reaching billions per square meter across the leaf surface. In homes located near heavy traffic, the plant was effectively filtering polluted air before it reached the wall itself. And that is where the entire public narrative surrounding ivy begins to collapse. For decades, people repeated the same warning. Ivy destroys buildings. Homeowners believed it. Neighbors repeated it. Entire HOA policies were written around it. But Historic England, the organization responsible for protecting some of the oldest stone and brick structures on Earth, spent 7 years and nearly 2,000 housing pounds trying to determine whether the fear was actually true. Their conclusion was direct. The aerial rootlets attached to ivy remain on the surface layer of healthy masonry. They do not penetrate intact stone or sound brickwork. On walls already in good condition, the ivy acts as a protective barrier against driving rain. It softens extreme temperature swings, responsible for expansion and contraction stress. It captures pollution particles that slowly erode mortar and limestone. It also cuts down the freeze-thaw cycles that gradually split brick and stone apart over decades. In other words, the common belief was not merely exaggerated. According to the research, it was reversed. There is, however, one important warning, and it matters. If the wall is already damaged, the situation changes completely. Existing cracks, weakened mortar joints, or open gaps inside deteriorating masonry can allow ivy growth to spread deeper into those weaknesses. In that situation, the plant can absolutely accelerate structural damage, which means the rule is surprisingly simple. When the wall is healthy, ivy protects it. If the structure is already failing, repair the damage first before allowing the plant anywhere near it. That single distinction explains why the myth survived for so long. In many cases, the wall was already deteriorating before the ivy ever touched it. Later, when the structure worsened, the plant took the blame. But what is actually happening here? The numbers are dramatic, and the physics behind them matters because 3 separate mechanisms are operating at the exact same time. Any one of them alone would already provide a meaningful benefit. Combined together, they create something mechanical. Cooling systems still do not truly duplicate. The first mechanism is straightforward: shade. A thick canopy of leaves intercepts direct sunlight before solar radiation ever reaches the exterior surface of the wall. That part seems obvious. Yet ivy performs better than a normal shade barrier. Researchers who compared ivy against a standard shade sail discovered something surprising. Even when both blocked an equal amount of sunlight, the wall protected by ivy remained 7 degrees Celsius cooler than the wall behind the artificial cover, which leads directly to the second mechanism: evapotranspiration. The plant effectively perspires. Moisture rises from the soil through the roots, travels upward inside the stems, then exits through the leaves into the surrounding air. As that water evaporates, thermal energy is pulled away from the environment nearby. It is the same cooling effect you feel on your own skin after stepping out of a shower. The vegetation is not merely preventing sunlight from striking the wall, it is actively cooling the air itself in front of the structure. No power cord, no electrical draw, only water, sunlight, and biology doing the work. Then comes the third effect, the trapped air layer. Between the rear side of the leaf canopy and the wall surface sits a narrow zone of still air. And still air is one of the most effective insulating materials in existence. The principle is identical to the design behind double-pane windows. It is the same concept used in those Velcro-sealed curtain systems. Heat encounters a motionless barrier it must slowly penetrate instead of flowing freely into the structure. Shade, evaporation, motionless insulating air. 3 different cooling processes operating together inside a single living organism powered entirely by sunlight and water for $5. Now compare that to the economics of modern siding. Replacing siding on a standard American house usually costs somewhere between $10,000 and $17,000. Yet the material itself does nothing to cool the wall. It provides no summer thermal buffering. It does not clean pollution from the surrounding air. It does not reduce temperature fluctuations, striking the structure. It simply absorbs solar heat all day long and transfers much of that energy directly toward the interior living space. Then, after 20 to 30 years, the entire cycle begins again because the siding must eventually be replaced. An ivy plant costs around $5. Within 2 to 3 growing seasons, it can fully spread across a wall. Properly maintained, it survives 30 years or even longer. No operating expenses, no maintenance contract, no replacement schedule, and unlike standard siding, it actively cuts the summer thermal load entering the house by roughly 1/3. During winter, it also adds insulation value. For a household spending about $1,300 every year on heating and cooling, that translates into hundreds of dollars returned annually throughout the lifespan of the plant itself. Nobody launched a campaign against ivy. The real issue is far simpler. The plant has no major branding machine behind it, no high profit margin, no recurring replacement cycle, no yearly service subscription. It sits quietly in the garden section at Home Depot, only a few feet away from displays advertising $12,000 worth of James Hardie fiber cement siding. And almost nobody realizes those 2 products are competing against each other. Then there is the HOA problem. Across the United States, homeowner associations routinely prohibit climbing vegetation. The justification almost always centers around structural damage to walls. Ironically, that is the exact claim the research challenged and largely disproved. In practical terms, some HOA rulebooks may effectively require homeowners to leave the largest sun-exposed surface on the property completely bare, fully unshaded, and directly exposed to solar radiation year after year. Then the homeowner pays every month to remove that accumulated heat using an air conditioning system for the rest of their life. The pattern feels familiar. It resembles the same HOA policies banning white roofing materials while demanding darker earth tone colors instead. Those darker surfaces absorb far more heat from sunlight directly into the structure. And then comes the invasive species concern, which is absolutely legitimate and deserves serious attention. In 2010, Oregon prohibited the sale of English ivy. Washington followed with similar action in 2025. Across the Pacific Northwest, English ivy can escape residential yards and spread into forests. Once established, it climbs native trees, blocks incoming sunlight and destroys understory ecosystems within only a few years. In that region, the environmental threat is real, but that same characteristic is also what makes the plant so effective on a building. Its aggressive growth, rapid spread, and extreme durability are precisely the traits that allow it to function as a thermal shield on a wall. With trimming only once or twice per year, the plant remains controlled and stays where it was planted. And in the Pacific Northwest, homeowners simply use Virginia creeper or Boston ivy instead. The issue is solved. Meanwhile, throughout most of the United States, English ivy remains fully legal, widely sold, easily available, and almost completely overlooked. Now imagine this. It is August. It is 3 o'clock in the afternoon during August. You walk beside the south-facing wall of your home and place your hand against the exposed siding. Instantly, you jerk it away. The surface feels blistering hot. Even standing 6 inches back, you can still sense heat pouring outward into the air. Then, you move a few steps sideways to the section covered in ivy. You slide your palm behind the leaves and touch the wall underneath. It is not lukewarm, not merely less hot. It is genuinely cool beneath direct afternoon sunlight. The air trapped between the foliage feels calm, shaded, almost soft against your skin. You pause there for a moment and suddenly notice something else. The air conditioner compressor is silent, not because the system failed, because it no longer needs to cycle constantly. That wall has stopped pumping heat into the house, and that is the exact instant the conversation changes. The numbers stop being abstract statistics and become something tangible, something you immediately want for yourself. So what does installing a system like this actually involve? The surprising part is how uncomplicated it really is. The first decision is choosing the species, and that choice matters. English ivy, Hedera helix, remains evergreen throughout the year. Its leaves stay in place through winter conditions. That means cooling during summer, insulation during winter, and continuous wall protection in every season. It functions as a year-round thermal shield. But another option exists, and it behaves in a remarkably intelligent way. Virginia creeper and Boston ivy are deciduous plants. During spring and summer, they develop a dense canopy of leaves, full shading, full evapotranspiration, full cooling performance. Then autumn arrives, and the foliage falls away. Suddenly, the wall becomes exposed again to the lower angle winter sunlight. That means free solar heating directly into the structure precisely during the season when warmth is valuable. Once spring returns, new leaves emerge again. Cooling resumes automatically. The plant essentially changes operating modes with the seasons. No thermostat, no timer system, no smart home controller, no motorized shades. Just biology responding naturally to daylight length and temperature shifts, while accomplishing automatically what modern automation systems attempt to imitate with electronics. Place the vine at the base of a south-facing or west-facing wall for the greatest cooling effect. On surfaces made from brick, stone, stucco, or concrete, ivy attaches naturally by itself. Tiny aerial rootlets grip the exterior and climb upward without assistance. No wireframe, no trellis, no support hardware. You dig a small hole, set the plant in place, water it, then leave it alone. That airflow matters. One ivy plant usually spreads across roughly 10 to 15 feet of wall width. Early growth averages around 1 to 3 feet each year before accelerating later. Most walls reach full coverage after 2 to 3 growing seasons. For homeowners wanting faster results, planting 3 or 4 starter vines about 18 to 24 inches apart along the wall base can dramatically speed the process. Total cost stays around $15 to $20, and meaningful coverage may appear before the first summer even ends. Maintenance requirements are minimal. Trim the growth once or twice annually to keep it away from gutters, windows, and roof edges. That is essentially the entire workload. There is one honest limitation, though. Results are not immediate. An air conditioning system begins cooling the same day it is installed. Even with several ivy plants growing together, one complete growing season usually passes before meaningful wall shading develops. That delay is real, and it explains why many people default toward mechanical cooling systems instead. But compare the trade-off carefully. The average air conditioning unit costs around $5,000. It survives perhaps 15 years while continuously consuming electricity the entire time. The plant costs $5. It can survive for 3 decades. Rain keeps it operating. At this very moment, there's probably a wall on your house that sunlight has been heating since 7 o'clock this morning. Since 9 o'clock, your air conditioner has been struggling against that heat transfer. The compressor keeps cycling on and off. The electrical meter continues spinning. Meanwhile, sitting inside a garden aisle only 5 miles away from your home, inside a simple 4-inch pot beside hostas and ferns, there is a plant that could have intercepted much of that heat before it ever touched the wall. $5. No permit required. No wiring. No monthly bill. The Romans planted ivy across their villas centuries ago. The colleges of Oxford have covered their buildings with it for generations. Historic England spent 7 years gathering evidence proving the plant helps protect the structures beneath it. Yet somewhere down the street, an HOA still bans it because somebody once repeated the claim that ivy destroys walls. The research points in the opposite direction. The solution has been sitting on the shelf this entire time. What has been missing is simply someone willing to point at it. If stories like this matter to you, stay with us. There's much more ahead. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.